Can you guys hear me okay? All right. So thanks for having me. It's a pleasure to be here. And thanks, Jared, for introducing kind of the first half of how we achieve images of directly imaged planets, how we get these things. As I was listening to Jared talk, it occurred to me that maybe I should add one slide to start and hopefully wake everyone up a little bit. If I can make it advance. Okay, there we go. Let me give you the outline of my talk first. I added one slide in just a second. So essentially, Jared just talked about all the hardware techniques that we use to directly image planets. And so I'm going to talk about how we use observing strategies and post-processing techniques to get kind of the extra few orders of magnitude and contrast that we need in order to see the light directly emitted from giant exoplanets. And I'll talk about how we separate, once we do see a signal, how we separate potential false positives from real planets. And those kind of come in two different families. There are astrophysical false positives, and then there are some instrumental false positives that we can have. But I added this one slide to start because it occurred to me that I should give you guys some context. And I want to wake you up a little. So I would actually like you to talk to your neighbor. Let me give you some context here first. But so this is the current exoplanet landscape. You've probably seen a couple plots like this in the last couple days. These are the different imaging techniques or the different planet detection techniques that we use, where the directly imaged planets are in red here. And my question to you is, based on this plot, what occurs to you about these planets? And in particular, I give talks pretty frequently. Actually, I give talks to scientists about why they should care about direct imaging. I give talks to the public where I show them this slide, and they always say some kind of snarky things about direct imaging. And I'm wondering if you guys can guess what they are. So talk to your neighbor and see if you can come up with what you think the public says disparagingly about direct imaging. No, my students are watching, so yeah, yeah. All right, what do you guys think? Throw it out. What's all the, I mean, you guys have heard all about RV and transit, and they're awesome. What do you think people say about direct imaging? Yeah. Look at all these interesting planets. Sure. What else? Yeah. Absolutely. Well, actually, why are you doing any of these techniques then, right? So no, that is definitely a point that they make. Yep, that's one of the first things they notice is we aren't detecting any of these. So often they assume that means we're special, right? So we have to talk about selection biases and all kinds of things. Anything else? Any other like bad things? Yep. Yeah. Okay. I mean, of the cool planets that we've discovered that don't exist in our own solar system, I think we can all probably agree that like the super Earths might be the more interesting, that the hot Jupiters might be the more interesting, and these distant super Jupiters, well, they're not the, you know, every planet is special, just like every child is special, and these are really, really interesting planets, and I hope that you guys will be convinced by that, by other talks like Travis's talk. Sort of the point that I wanted to make just at the beginning here is that the reason you should care about direct imaging is because this is the path forward to characterizing planets. It's a direct technique, so there is kind of like a visceral satisfaction advantage to direct imaging where we actually get to see the planet, and we all like that. But the principal advantage of it is that it's capable of characterizing the planets, that we can break the light that we receive from it into its component colors. We can find out things about its atmosphere, and that in moving forward, in applying the kind of techniques that Jared was just talking about in space, this is the path to characterizing an exo-Earth in the future. So there's a bright future for this technology, and these planets are interesting and special, I promise. So just a little bit of context. So to start, I want to just give you some terminology about these things. So Jared mentioned a few of these, but I'll just reiterate. So the first one is contrast. That's the ratio in brightness of the planet to the star. We talk a lot about high contrast imaging. So high contrast in the context of what we're doing right now means kind of like 10 to the minus 6. So a factor of 1 million difference in the brightness of the star and the planet. We talk a lot about the point spread function. You guys have all probably encountered the idea of a point spread function before. You know, in principle, in a perfect telescope, this would be an Airy pattern, but in reality, it's much more complex. And in addition to being complex, it's time dependent. So things are changing, and you'll see some movies of how that works. Jared introduced the idea of a speckle. So, you know, they're essentially images of the star that are introduced into the images, and those are our principal sort of potential sources of confusion. There are things that can masquerade as planets, and so a lot of what I'll be talking about is techniques to distinguish a speckle from a real planet. Post-processing, which is what most of what I'm going to be talking about, is anything you do to suppress the light from the central star as effectively as you can. And just one other piece of terminology that we may throw out here in my lecture and maybe some others is the idea of inner working angle. So how close can you get to the star and still separate out light from the planet? Okay, so to summarize, well, to kind of give a little summary of Jared's talk in one slide, what we do right now in terms of hardware is adaptive optics and coronagraphy. So here's this is the point spread function of the Gemini planet imager, unocculted, so no coronagraph. And here is what the PSF looks like. So this perfect PSF that you see kind of in gray in the background here is a perfect Airy pattern. And here in principle, or here in practice, is what we get with the Gemini planet imager. So you see that with adaptive optics, with a really good instrument, you can start to kind of approximate an Airy pattern. This axis here is essentially contrast. So one thing I want to highlight is, if you look, just with adaptive optics, you know, at half an arc second, you could get to contrast of 10 to the minus 3, maybe, right? With a good AO system. With coronagraphy, you can push that down another few orders of magnitude. So you can see even fainter things there. But here's kind of the landscape of what we've done so far. So this is a plot from Brendan Bowler's paper. So Brendan Bowler wrote a review paper on direct imaging a couple years ago. And if you're just getting started in the field or you want to know more about direct imaging, this is where I'd suggest you go first to learn about it. But this is sort of the landscape of all of the directly imaged exoplanets are points here. Some of them are really brown dwarfs, but brown dwarfs are interesting too. So this is what happens to them as a function of age. And this axis is essentially contrast. So one thing that I wanted to highlight is sort of, oh, and these tracks in the background are cooling tracks for planets of different masses. So Jared mentioned that what we detect mostly with direct imaging are young planets that are still giving off thermal emission from the formation process. So this is a 1 Jupiter mass planet, 2, 3, just cooling with time. So if we want to get down to kind of the most interesting planets, we have to get to at least contrast of 10 to the minus 5, really kind of more like 10 to the minus 6. And there's sort of AO plus coronagraphy can get us to this 10 to the minus 3, 10 to the minus 4 range. But we have to get several orders of magnitude better than that if we want to actually see the planet, right? So how do we do that? So it's all games, again, about separating the light from the star and the planet from, separating planet light from speckles. So here's a movie. So here's the first thing that you can do. So you can leverage angular diversity. So I like this movie because it shows, so this is a Gemini Planet Imager, observations of the debris ring around the young star, HR 4796. So you see a few different things here. So first of all, you see the PSF of the central star is changing a lot. So there's a coronagraph in there, which is why you see kind of a hole. These are what are called satellite spots. We inject them into the image on purpose in order to do astrometric and photometric calibration. Those stay steady in what we call the instrument frame. And if you look at this image, you'll see that there are lots of things that stay steady in the instrument frame. For example, there's a speckle right there that stays constant throughout this exposure, or it changes a little bit in brightness, but it stays in the same place, right? And the disk, this ring here, this is a real astrophysical object, a ring of debris, of dust around a young star. And what we've done is we've turned the instrument rotator of our telescope off. And when you tell like extragalactic astronomers this, it kind of breaks their brain because they're like, why would you do that? But the point is that most of the sort of artifacts that that are induced by the variable atmosphere, by the optics of the telescope, are static in what we call the instrument frame. But real astrophysical objects rotate with the sky. So we can leverage this rotation in order to separate real signals from potential false positives. So kind of the classic way to do that is using a technique called angular differential imaging. And I think the easiest version of angular differential imaging to understand is classic angular differential imaging. So here's a cartoon picture of a complicated PSF. There's some speckles in there, and there's a planet. So you are taking multiple exposures. Your PSF is staying mostly the same. Your planet is moving from frame to frame. So the first order, one thing you could do is a simple median combination of all of these images. And what you would expect to do is capture the instrumental PSF, but not the planet, because it's never in the same location in these frames. So then you could take this median PSF, you could subtract it from each individual one of these images, and you'd have some junk left at the middle, because of course it's not going to be a perfect probe of the PSF in each one, but you'd suppress a lot of the starlight, and then you'd have the planet in a different location in each one. So of course there's an additional step here, but luckily we understand the geometry of the Earth's rotation pretty well, so we can derotate all the images to a common on-sky orientation, and then stack them again with a median, and that will suppress the residual starlight further. So that's classical angular differential imaging, and this is how the first directly imaged exoplanets were discovered using this technique. So here's just, I like movies. So here's another movie showing, again, this idea. So here's GPI again, but instead of a disk this time, we have a planet. Does anyone see it? You guys see it right here? So it's moving through the images with time. So what we do in practice these days, so I mentioned that, for example, if you just take a median PSF, that's not going to be a good estimate of the PSF of the star for any given frame. It'll do kind of okay. But we can use more sophisticated techniques to estimate the PSF of these in these images. And they kind of fall into these two families. Here are some references that would get you started learning about the techniques. These are kind of the original papers on these two techniques, but there are lots of papers now on how they work. So I'm just going to talk about CLIP. Loki is sort of functionally equivalent, although the exact mathematics of it are a little bit different. So CLIP is a principal components technique. And honestly, I find principal components analysis easier to understand in the context in which you see it used the most frequently in the literature, which is actually in social science. So if you do something like survey a bunch of people, you give them a bunch of questions. One thing that you could do is look for kind of fundamental underlying characteristics of this group of people based on the patterns in their answers to different questions. So for example, I am really interested in students' math anxiety in classes. So if I give them a survey asking them a bunch of questions about their attitudes towards math, you might expect them to answer similarly on similar questions, right? So principal components technique is just looking for patterns, in this case between questions on a survey or something, and picking out the things that vary together. So geometrically, this kind of looks like looks like this. So what you're looking for is, so this is just a two-dimensional parameter space, but here's an answer to one question, an answer to another question, say, or the value of one pixel and the value of another pixel. What you're looking for are these principal components. So you're looking for axes along which sort of you can describe as much variation as possible. And if you imagine it in so say like a three-dimensional parameter space, there would be some sort of vector that you could carve through that space. But we're talking about a very complex, very multi-dimensional parameter space. And so if you try and think about it geometrically, it can kind of break your brain a little bit. But this is the basic idea. In preparing for this talk, learned that this is actually a really common technique in facial recognition. And I thought this was a good example. So these are eigenfaces. So if you feed a bunch of images of human faces to an algorithm like this, it'll pick out, like, this is the first principal component. This is the most common sort of set of pixels that vary together. So if I wanted to subtract eigenfaces and then like show unique features in my image, I could, scale this image and subtract it. I could also build a face out of combinations of these eigenfaces. So it's similar, actually, in how we do this with exoplanets. And what we're essentially doing is we're taking a library of reference images, so other images in the sequence. So for example, here, so here's an image, and say there's a speckle here, and there's also a planet here. So I'm marking the location where this started. Sorry, so this is just a planet. So I'm marking the location where it started, and I'm marking where it is in each of these images that are farther along in the time sequence. So one thing that I could do is I could pull all of these reference images together, and I could look for common patterns in them. And if you look at this, you can see that there are some very common patterns. Even though the images are changing, there's this, say, wind butterfly here. So there are things that appear in all of the images. So I could build a custom PSF for every individual image in my cube that is my best guess at what it shares with all the other images that I've given it as references. And then I can subtract it and hopefully have my planet. So one thing about how this works is that essentially, you have a star and you have a planet. We're doing ADI, so we're allowing it to rotate. We have some rotational space to work with over the sequence of exposures. So if I take like an image in the middle of the sequence when the planet is here, one thing that you struggle with is this idea that you want to include reference images that are close in time, because those are the most correlated reference images, but you also want to avoid having the planet overlap with itself in those images. So what you do is you have something called a rotational mask. So you apply some minimum rotation before you're going to include all the images in the references. So you can do that forwards and backwards in time. So maybe I require that it moves by one full width half max or something. So moving forward in time, any images where the planet would be at least here or further along, I'll include in estimating my PSF here, or I can go backwards in time and do the same thing. So this idea will become important in a minute. So that's trick number one, angular differential imaging, or leveraging angular diversity. Trick number two is spectral diversity. So this is a raw image from the Gemini Planet Imager of Neptune. And if you zoom in on it, GPI is an integral field spectrograph. So these are not individual pixels. If you it's like those magic eye pictures. If you kind of defocus your eyes, you can convince yourself that this is just sort of an image of Neptune. But in reality, it's a bunch of microspectra. So what you can do, if you zoom in on these, is leverage the spectral information that you get. So what the Gemini Planet Imager reduction pipeline does is it takes this image and it constructs a cube of images where the third dimension is wavelength. And you can see that there are features on the surface of Neptune that get brighter and dimmer at different wavelengths. And this is true for exoplanets too. So here's kind of the biggest, the lowest mass exoplanet directly imaged to date, one of the really important ones, 51 Erie. The planet is here, And this is walking through the spectral dimension of the cube. And what you can see is there are wavelengths where you can't see it at all, and there are wavelengths where it's very bright. So one trick that you could use is leveraging the wavelengths. And by the way, these correspond to absorption bands of molecules in the atmosphere. So water on this side and methane on this side. This is H band, so around 1.6 microns. So you could leverage wavelengths where the planet is dim to estimate the point spread function for the wavelengths where the planet is bright, right? And avoid this problem of having the self-subtraction. So here's a movie of that, of kind of how that would work, about how you could, and this should help you realize how we can separate speckles from the planet. So this is the same cube that we showed you before, where the planet was walking around. But in this case, it's just one image, one time step, but where the planet will stay here, and you'll see that the features of the point spread function will move out. That's just because the location of things like speckles scales as lambda, lambda over d, really. So what's happening, what you could do then is you could do kind of in the same way you do it with angular differential imaging. You could scale all of these to a common instrumental orientation. So you could like take ones where the speckle has moved out and scale them so that it overlaps. And in that case, what you've done is you've moved the planet. And you could construct a point spread function from other wavelengths and subtract it, and then you could rescale back out to move the planet to where it's supposed to be. So a problem with all of these techniques, both angular differential imaging and spectral differential imaging, is over self-subtraction. So in practice, you can never, particularly when you have features like this that are extended, you can never really create a library of reference images where there is no emission from the object. And so what comes out at the end of one of these principal component reductions is something that has the object, but it also has sort of shadows due to what's called over or self-subtraction. And I mentioned before that what you really want to do is leverage the most similar PSS in the time sequence. And those are the ones that are closest in time, generally, which means sort of necessarily what you want to do is set this is what we call rotational exclusion or rotational mask. You want this to be aggressive in a lot of cases in order to remove the starlight effectively. So you're always going to have to deal with self-subtraction. But we actually have some techniques. Oh, and here's what it looks like with the planet. So this direction, by the way, is the angular direction, and this direction is the spectral direction. So you've leveraged some wavelengths where this planet is not as bright, but there is still some self-subtraction. It still exists in some of the other wavelengths, just more faintly. And likewise, you've excluded reference images where the planet is in exactly the same location, but you've allowed it to be just a little bit farther along. So you'll get this sort of characteristic shape for real point sources in your images. And we can leverage that because it's something that we can predict. So I think actually I included that a little bit later. So I'll just mention this and I'll come back to it in a few. Oh, I did put it here. Good. Okay, so here's the original model. Here's the CLIPS data with the self-subtraction. If you keep track of the mathematics of CLIPS, you can actually create a forward model that shows you, based on what principal components are extracted, what something should look like when it comes out. So you can do this for point sources, and you can do this for extended emission. So this is a form of vetting, really, right? If this is what we think it is, we think it should come out of the backside of CLIP looking like this. And it does, great. Okay, so that's one form of vetting. Now I'm going to just turn 90 degrees and talk about another form of vetting of planet candidates, which is what we call common proper motion. So you guys all probably in college astronomy classes encountered the idea of parallax, of course. So if you have a bunch of very distant background objects, so one thing to know about all the directly imaged candidate planets is that they're around relatively nearby stars, so stars that should demonstrate parallax. So if you have a field of distant background stars and you have a star in the foreground relative to Earth with a planet, what should happen with time is they should move together relative to the background star. So one thing we worry about a lot in direct imaging is having, say, a distance. So generally we're looking at kind of red things. We're looking for things that are cooler than, you know, G stars or A stars or whatever it is that we're looking at. But you can have like distant red giants on the other side of the galaxy with similar colors to an exoplanet. So what we worry about is separating those distant background objects from actual bound companions. So we try and watch them move together through the galaxy. So I'm going to, for the rest of the talk, just give you a couple of case studies. So here's a case of a directly imaged planet candidate around HC 131399. So there's the candidate. It's in this really interesting triple system. So there's a binary M dwarf system here. Here's the primary star, and there's the planet. Eric Nielsen wrote a paper on this following up the discovery paper. And here's the reason why this was believed to be a real planet. So just to break down this plot a little bit. So this is time on this axis. And I'm showing position angle. So like the angle between north and where the planet is detected, and the separation with time. And this track here, with the wobble, is kind of what you'd expect for a faraway background object relative to the primary star. And the reason it has this shape, this wobble here is parallax, because the foreground star is wobbling as the Earth orbits the sun, and this sort of trajectory is the proper motion of the foreground star relative to the background one. So if you had a distant, infinitely far away background object, you'd expect it to fall in here. And look, this doesn't fall in there. So these are the data points, the astrometry for this companion. If you were just looking at position angle, it looks okay, like it follows the background track. But in separation, it's not quite doing what it should, which is a little strange. But it's also, you'll notice, not following. So what you sort of to first order expect for both separation and PA for these slow orbiting companions is that when you come back in a year, it'll be at roughly the same PA and separation relative to the star if they're moving together through the galaxy. So these are bound orbits, and it's not there either. So the solution here turned out to be that this is a non-zero proper motion background object. So it's a background object. It's close enough that it does have some parallax in proper motion, but that parallax in proper motion is distinct from that of the star in the foreground. And I'll come back to this object. So one of the things I'd really like to highlight about doing this and vetting planet candidates is that when you're working at the hairy edge of a technology, you're going to make mistakes, and that's totally understandable. Someday you guys may publish some things that will turn out to not be real, but that's the nature of our field, and it's important, and shouldn't feel too bad if that happens. So here's a case where it worked. So this is the star HC 95086, and here's the primary star behind a chronograph. Here's a background star in the field. So this is a slightly different way of looking at the same thing, but essentially here's the initial detection, and here's the prediction for where a background object should be, and here's where this background star appeared when they came to follow up this system. So they overlap. This is a background object. The planet candidate started here, and it should have been here if it were a background object, but it actually is in pretty much the same place that it was. So this is an example of a successful sort of common proper motion validation of an exoplanet candidate, and all the other ones have been validated in kind of the same way. So this is a common technique. One other kind of exciting thing that if you have a long time to do it, that helps validate a planet candidate is, of course, real planets bound to their stars should orbit. So if you do this over time, if you monitor them over time, you should see nice orbits. So here's Beta Pic, which is in a nice edge-on orbit. the HR 8799 system with all 4 planets. This is 51 Erie. So, you know, common proper motion is the first thing, but then there's an additional validation with time that's kind of that they are in bound orbits around the star, and we are starting to be able to do this with these directly imaged exoplanets. So spectral validation is kind of the other thing that we want to do. So these are all the directly imaged exoplanets with the Gemini Planet Imager, and the only reason I show this slide is just to stress that these are cool objects and they have complex spectra, right? So warm objects have fairly simple spectra. They're black body-ish, right? Complex cool objects have absorption features in their spectra. And so you can see that all of these sort of validated planets and brown dwarfs have, I guess these are all the planets, have complex features in their spectra. So you could use this as a technique too. So this was the other piece of that 131399 paper, was that the spectrum of that candidate planet is flat, or very close to flat. And so this is, I think Travis will talk a little bit more about this, but the spectrum is definitely a tell regarding the temperature of the object and its composition. So, and this is a way that we can distinguish things that are real from things that aren't. So the last sort of potential source of false positives, and the one that's nearest and dearest to my heart, is, well, when we look at young stars, they also have debris disks. They have debris disks, they have protoplanetary disks, they have transitional disks, they have lots of gas and dust left around them. And that gas and dust, it turns out, the more and more high contrast imaging that we do, has very complex structure. So these aggressive processing algorithms that we use, they can be somewhat problematic in this context. So here's an example from a paper of mine from last year of a really interesting complex transitional disk, so a disk with a cavity at the center. And these are different methods of processing it. So this is that classical angular differential imaging that I talked about. This is the angular differential imaging images with some other post-processing, what's called a high-pass filter. And these are those two kind of aggressive processing algorithms that I talked about. So I could, you know, give a whole talk about this, but the one point that I want to make here is that as aggressiveness increases, so does the clumpiness of the structure. So in particular, if I zoom in over here, you can see that I can make points out of it. So this is just something that we have to be aware of, and we have to work to characterize. So there are a few different ways that with a system like this, you can validate a planet candidate. So one of the classical things is just, if I see it in classical angular differential imaging, even if it's at lower signal to noise than in the aggressive techniques, pretty good. Like if I see it with multiple techniques, it's probably not an algorithmic artifact. Of course, it could just be disk. You could have some sharp disk feature that that can masquerade as a planet. And in this case, the spectral information that we get, we can use. So there is a planet candidate at this location in the disk. So what we did is we took an aperture kind of in a place that's unambiguously disk, and we compared the spectra at those two locations and to the spectrum of the star. And you can see they all have very similar structure. So dust grains scatter light from the star as approximately in sort of a gray process. So they, you know, they'll just, dust grains should have the spectrum of the star. And so we can leverage that spectral information to separate potential disk contaminants from real planets. There was actually another candidate planet kind of in here that showed a similar thing. So that's one way we can validate a candidate. We can also leverage wavelengths where we don't think that planets should orbit. So, you know, I'm biased, but I think that these embedded planets are the most interesting ones, right? It just tells us something about the planet formation process. And so it's worth trying to come up with techniques that will allow us to separate light from planets that are in systems that are this complex. So this is hydrogen alpha light around the young star lit calcium-15, which has a disk component out here kind of in the image, and there's actually a disk component in here too. So here's what it looks like at H alpha. here's what it looks like in a neighboring wavelength where we expect there to be only starlight and scattered light from the disk. And if we take the difference between these two, this is a form of spectral differential imaging, then you can see that this object pops out. So this is a real object because, well, H alpha emitting background objects are extremely rare, right? So just the probability of having this be a spurious detection is pretty low. Of course, it could be an instrumental artifact. So the reason that we think this one is real, I'll mention we weren't able to do common proper motion because we were weathered out the second time we went to look. But we did end up publishing this because there was another, it was detected at the same location at another wavelength. And that object was shown to have common proper motion to do like appropriate orbital fitting based on sort of archival images as well. So in this case, the spectrum is distinct from the star and it's detected at multiple wavelengths. So I just sort of cherry picked a few examples, positive and negative examples of things that were or weren't planets. We could talk about this all day. I hope you guys have some questions. I just want to leave you with a summary of how you know it's a planet in the context of direct imaging. So it should rotate with the sky if you're doing ADI. It shouldn't change its location with wavelengths, unlike the speckles. So that's going back to this movie where the planet was staying the same and the speckles were moving in and out. It should move with its star, so it should have common proper motion. Its spectrum should be distinct from the star's spectrum because it should be a much cooler object. And it should be robustly detected with multiple PSS subtraction algorithms and multiple sets of algorithmic parameters. There are these things that you can tune in these aggressive processing algorithms. And the stability of the planet to different choices of parameters is also very important. So I'd be happy to take questions. Oh, when we get to contrast of 10 to the minus 10? Sorry, so I think the question was when we are pushed towards reflected light planets, which require contrast of things like 10 to the minus 9, 10 to the minus 10, will we worry about contamination by background objects like galaxies that are at similar contrast? Yeah, but yes, but these techniques will serve us well in this context as well. So you wouldn't expect a distant background galaxy to have common proper motion, for example. Yeah, great question. So the other sort of, oh, sorry, thank you. The question was essentially how does direct imaging and transmission spectroscopy compare in terms of what we're sensitive to and how it works. And transmission spectroscopy is the other technique that's capable of characterizing planets, but I would say they're very complementary because, of course, transmission spectroscopy only works if you have a transiting planet, and those are sort of by geometric reality. The geometric reality of it is that those are very close in planets, and those are we're not going to be getting with direct imaging in the near future. You learn, I don't know like a ton about transmission spectroscopy, but you learn kind of similar things about the atmosphere. Although, you know, transmission spectroscopy can constrain things like it's essentially constraining the scale height of the atmosphere, right? So how big does the planet appear at these different wavelengths? And so is it cloudy? Is it clear? Some about its composition, the composition of the atmosphere. So I'd say it's sort of similar information, but maybe Travis can speak to that more in his talk. I mean, so it depends a little bit. So you know, I showed you guys a movie of beta pic moving through raw images, right? So you can separate it with raw images. In the case of things that are at the very hairy edge of what we can detect, we have to be pretty aggressive. And so self-subtraction, I mean, it depends on how quickly your PSF is changing in time and sort of by what kind of factor. So generally speaking, in order to pull out the faintest planet signals, we have to be fairly aggressive. So self-subtraction is definitely, you know, if you look at all the published direct images of exoplanets, you'll see this self-subtraction now that you know about it. So it'll have this characteristic 2 dark lobes on either side of it. And in case of SDI, an additional one in the sort of radial direction as well. Yeah, so whether they're artifacts, sorry, thank you. It's like I have a mental block on this. So the question was, essentially these aggressive processing algorithms, can they induce spurious structure when you process something that's very complex with them? And I would say yes, and it sort of remains to be seen. I mean, certain things like sharp rings, those are pretty easy to pull out. So sharp features in general, these algorithms act almost like a high-pass filter, right? So they will pull out sharp features in what you're looking at. And so they tend to pull out what we think is real structure, but if you have too much overlapping real structure, then the self-subtraction of, say, one spiral arm, if it overlaps with the other spiral, you can have trouble extracting what's really there underneath. And so I would say sort of we're kind of just getting to the point of trying to do it. And the common technique with disks that lets us validate structure is something called polarized differential imaging, which is very complementary. And I haven't talked about it in any detail, but structures that we see in polarized light, which scattered light from dust grains should be preferentially, those, if you see those in polarized differential imaging and you see them in the aggressively processed images, then that's sort of like an additional validation. So to validate disk structures, we do multi-wavelength imagery. We try and see what we see when we are processing aggressively and not so aggressively, and then we try and use another technique, PDI, in order to validate them. But it's tricky.
Thank our speaker again.